Okay, so the last thing we talked about was, um, you know, mutual inductances, linear transformers, and transformers. And so today we're going to look at some example problems using those particular things. So first off, let's start off with what's problem 1321 in your book. Okay, so this particular circuit has, I think, pretty much everything you would sort of need to know with mutual inductances. It's got several inductors here. And in addition, it has the mutual inductance going all over the place. Now I'm going to do something that I think is a little strange here. They call this current I1 in the book, and I think what they're after here is maybe it's just the voltage or current. I actually don't have my book, but I think it may be just what are the mesh currents in this particular problem. So maybe it's just I1 in fact by itself. So this is a 4 ohm inductor. This is a 4 ohm resistor, a 4 Henry inductor, a 5 Henry inductor, a 6 Henry inductor. This is 6 ohms, and this is 5 ohms. And so this is 100 cosine of 2t for the voltage source over there. So the first thing you need to sort of think of when you do this is you need to think of converting it to the phasor domain, just like we've done before. Now the other thing that we have to do here is we have to look at the mutual inductances and the dots. In this particular problem, the dots for these inductors, which are extremely important, are here, here, and here. So we have that. The mutual inductance between the 4 and the 5 Henry, remember, it can't, it needs to be related. It's got that coupling coefficient, but it can't be sort of like parallel resistors. You don't expect it to be more than square root. Well, I shouldn't say it's like parallel resistors. I should say that it's got a similar form, but it's related to those two resistance values, and they give it to you here, and you don't have to worry. I would either tell you the coupling coefficient, or I would just give you the mutual inductance. In fact, I almost always just give you the mutual inductance. And it's 3 Henrys between those two, and it's 2 Henrys between the 4 and the 6, and then between these two it's 0 Henrys. And so you might remember I talked a little bit about inductances and how you get the coupling. Those two inductors would likely have been put perpendicular to each other, so there's no coupling between the two. Okay, so that's this particular problem. Now the next thing I need to do is convert to the phasor domain. So I know with my setup here I have omega is equal to 2 radians per second, and the 4 ohm is going to go to 4 ohm. Same with the 5 and 6 ohm. They're resistors, so they stay the same. Now the inductances are going to be obviously different. So I have a 4 Henry inductor goes to J omega 4. So that's J2 times 4. So J8 ohms. And the others follow similarly. So the 6 Henry goes to 6 times 2 is 12 J ohms. And we have the 5 Henry is going to go to J10 ohms. Now that's not it, because notice we also have these mutual inductance terms that are going to be related to the 3 Henry and the 2 Henry mutual inductances. So we have that 3 Henry will go to J6 ohms. Remember, that's J omega M, where M is the mutual inductance, just like J omega L, but J omega M is going to be J times 3 times 2, so J6 ohms. And then, just to make sure that's clear, the 2 Henry will then be J omega M, which is J2 times 2 Henries. So that's going to be J4 ohms. Okay, so we've got those particular terms all converted to the frequency domain. The only other thing I have left is the 100 cosine 2t. So that is 100. Frequency is suppressed, and the phase angle on that is 0 degrees, so we have just 100 angle 0 degrees. So just to sort of reiterate, we could redraw this circuit if I want to, and I'll select it. And I'll paste it back here. And so now, the 4 ohm, all that stuff will sort of stay the same. I probably, in this particular case, I shouldn't have said I1 like that. It should have been really I1T. Now, though, since we were converting to the phasor domain, we do have this as 100 angle 0. The 4 ohm, the 5 ohm, and the 6 ohm resistors stay the same, but the 4 Henry ,5 Henry, 6 Henry, and the mutual inductors will change. And so, okay, we said the 4 Henry is now J8 ohms. The 5 Henry is J10 ohms. And the 6 Henry is J12 ohms. The mutual inductance 3 Henry is now J6 ohms. Mutual inductance 2 Henrys is now J4 ohms. And then this mutual inductance between the 10 and the J10 and J12 is J0 ohms. So there's no mutual inductance term there. Okay, now if I was defining everything myself here, I would go ahead and define my mesh currents. So since I1 is in this branch, it's the only mesh current in that branch, and so I'll also call this I1. And again, that's just because I want that mesh current I1 that I've defined will be the same as that branch current I1. I'll define I2 in the top loop, and I'll define I3 in the bottom right loop. Okay, so now the next thing I want to go back to is talking about how do we get the equations that we need. I really like using mesh analysis for these problems because it tends to work pretty nicely for the rules of the inductors. And what I mean by that is, let's go over here and talk about what we said with how I want to do things. Particularly, I'm going to copy this over here just so you can see. I think this is the most important thing with mutual inductances, and that is, let's not try to make things hard on ourselves. Let's label it so we never have to have any problems with sign convention when we're doing it. So I'm going to copy that. I'm going to come back here and go and paste it over here just so we don't forget our rules and I don't have to go back and forth, back and forth. Okay, so I'll move it over here. But remember, okay, so what oh, this was an example problem, excuse me. What I really want is not that, but just the description that I have here. So how do we figure out whether or not we have plus or minus signs is to look at, you know, these particular things. Does it satisfy the passive sign convention? What I mean by that is, you know, that is the voltage defined with the current going into it and so forth. Is the current entering the undotted terminal on the mutual inductance side? If it is, then add a negative sign. Is the plus on the self side with the dot or is it without the dot? So these are all the things we have to determine here for the mutual inductance terms. So I really like to look at that in particular because what I would like to say is let's make it work like we want. That is, let's make it satisfy the current going into the dot and so forth, and the voltages labeled properly for the pluses at the dot. And what I mean by that is, you know, let's say the book, for example, wanted to know this voltage right here, V. Well, that's fine. That voltage is with the dot, so I'd leave it that way. But what if they wanted to know the voltage right here across that 10 ohm? Well, I likely would not label it that way. I'd label it the opposite way because that voltage is not with the dot of that inductor. And then in the end, I would just flip the sign on the voltage that I got. And I think that's important to do because I think it makes it easier. So that's not what I would do. And what I would do is I'm just going to call this V4 Henry, and I'm going to label this one with the dot and call it V5 Henry. And I'm going to label this one with the dot and call it V6 Henry. And I'm going to do that because that will help satisfy that dot convention, and I don't have to worry as much about those conditions. The other condition I have to, satisfy is, is current entering the undotted terminal or is it entering the dotted terminal? Well, remember, we sort of know how to define mesh currents to go within a particular impedance. We know how to define it going one way in a branch. We also know how to define it going the opposite way in the branch as a sum of those mesh currents. So let's try to keep it such that our current that we use will always be going into the dot, and we can do our problem that way. So, okay. The first thing I would say is we've got to write equations as we go around here. And so what I would like to point out is, let's look at this first loop. I'm going to outline it in yellow here. So this is our first loop that we're going to go around. Notice we don't have any super meshes here. There's no current sources, so no super meshes. So now let's just write our equation. So if we write our equation, here's what we'll have. We're going to have, going through the negative sign, we'll have minus 100 angle 0. Now then we're going to go through that inductance. So what do? I'm just going to call it plus V5H. Okay, that's not the way we would typically want to do mesh analysis, because we would like everything to be in terms of the mesh currents. But I can back substitute all of that into my particular V5H term that I'll have, and I just think it's easier to keep it simple like that and not have anything messed up. So I'll say plus V5H, and that V5H is going to have both a self-inductance term and a mutual inductance term between both the 6 Henry, between both the 3 Henry mutual inductance term and the, well, I guess the 0 Henry mutual inductance term. It won't have one there. So then I'm up here at this particular point, and I need to go down through that 6 ohm. Well, the 6 ohm resistance is going to have I1 minus I3 going down through it, so plus 6 times I1 minus I3. And sum those up, it's equal to 0. And now, what I want to point out is, let's look at that inductance term that we've got here. We are trying to figure out what's going on with this J10 ohm inductance, and we know that I've defined here V5H is right there. And so, okay, the way I think you need to do this is, obviously we know that we're supposed to have V5H is supposed to be J omega, well, it's supposed to be the self term, which is going to be J10 times the current. Okay, well, the current going into the dot is just going to be I1 minus I2. And let's make sure we see that. So from this side, we see from the bottom mesh we have I1 going this way. From the top mesh we have I2 going this way. Well, I want my net current going into the dot to satisfy, we want it going this way, the net current into the dot to satisfy the passive sign convention, And so that net current is I1 minus I2. So I'll put I1 minus I2 here. And then we have the mutual term. And the mutual term is going to be J omega M, which we already saw for was J6. So I'll put J6. And remember, the sign convention says we need current entering the undotted terminal on the mutual inductance side. If so, add a minus. Well, let's not let it enter the undotted terminal on the mutual side. Let's make it enter the dotted terminal, so that way we don't have to put a minus sign there. And then we say, is it plus on the self side with the dot? If so, then you don't add one. If it's not with the dot, then you add a minus sign. Well, notice we were smart. We labeled all our plus signs with the dot. So we've got that covered. Again, I think that's the smartest thing you can do, is just, if it's not labeled that way in the problem, relabel it this way. Then you'll never have that issue, because you can always go and take the negative something at the end. Okay, so we've got J6, and we want the current entering into the dot of this one. And so into the dot, the only current in that mesh, in that branch, is the I2, and the I2 is entering the dot, so we are fine. And so we can say plus J6 times I2. Now, finally, I'm going to go ahead and be sort of a little bit stupid in some sense. We know there's a mutual inductance term between the J10 ohm inductance and the J12 ohm inductance, and it's J0 ohms. I don't need to do this one because it is J0 ohms, but I want to, just to sort of illustrate what we would need to do. So plus J0, okay, what would the current be entering into the dot there? Well, that current would be, okay, I3 is going into that, I2 is going against it, so going into the dot is I3 minus I2. Alright, so V5 Henry is equal to this J10 I1 minus I2 plus J6 I2 plus J0 I3 minus I2. So then what I could do is I could rewrite and substitute this equation there, and then it will look like a normal mesh equation. So I'll write minus 100 angle 0 plus V5H. Well, V5H is J10 I1 minus I2 plus J6 I2, and I'll go ahead and still put the J0 I3 minus I2, and then plus the last term is the 6 I1 minus I3, and that's equal to 0. Okay, so now that's that equation, and we're set up. All of it's in terms of the mesh currents I1, I2, and I3, and we are in good shape. Okay, so next let's go back to this problem and go through the bottom right loop. I'm going to come here and go around this loop. Okay, and so when I do that, I'll have, okay, 6 ohm, the current going up through that 6 ohm is going to be I3 minus I1, so 6 times I3 minus 1. Okay, the next step, now notice I labeled the plus of that V6 Henry with the dot of that 12 ohm intentionally. That's what you should do, and I'm just going to call it V6H and then back substitute it in. And then plus 5, okay, the only current in that 5 ohm is I3, so plus 5, and I3 is going the direction we're going, so this is equal to 0. So now I just have to solve for V6H like I did before for the V5H. So it's the mutual term. The mutual term, okay, I need the current going into that dot to satisfy the passive sign convention. I mean, not into the dot, into the plus. Since I've labeled it with the dot, it is going to satisfy the dot convention and the passive sign convention. Excuse me, I was not careful there. So J, that will be J12. And the current going into that dot, okay, I3 is going into it, I2 is going the opposite direction, so the current going into the dot, or excuse me, I should be saying into the plus, is I3 minus I2. Okay, now I've got the mutual terms that I've got to get, and the mutual term with the J4 mutual inductance between, you know, the 6 Henry and the 4 Henry above it. Okay, that will be J4. So maybe I shouldn't put J4 yet. I'll just put J4, not put the plus yet, excuse me. And okay, so what we've said is I need the current going into the dot of that J8 ohm. And the current going into the dot, well, there's only one current in that branch, and it's I2. So plus I2, and I2 is flowing into that dot. So that's all for that term. And then we've got the J0 ohm. So J0, and I need the current going into the dot of that one. And so the current going into the dot, well, I1 is going into the dot, I2 is going the opposite way, so I1 minus I2 is the net current going into the dot. And so I get to put a plus sign there. And that's V6 Henry. And then I can go and substitute that in my above equation, so I'll end up with 6 I3 minus I1 plus J12 I3 minus I2 plus J4 I2 plus J0 I1 minus I2. So that's all for the V6H plus 5I3 equals 0. Okay, so that's my second equation. Then I got what's going to be the longest equation that I have to write for that top loop. So we've got to write the equation here. Now notice this one's going to be a little bit different from what we've had so far, because every time we've written our equation so far, we've got the dot convention and we've been going, you know, the way we've labeled the voltages. We put the dot with the plus, so we've added all the, you know, voltages that we've done since we've gone clockwise around those two loops. But that's not going to happen this time. So let's make sure we understand how we're going to get this. Okay, so I'm going to start here and go up and around. And so the first thing I've got to write is, obviously we're going through that resistance, so I need to write 4. The only current in that resistance is going that direction as we defined it, so 4 times I2. Okay, then what I would say you need to do, right, we labeled that V4 Henry, then we labeled the next voltage V6 Henry and the next voltage V5 Henry. So what I would do is just label it those voltages. Don't mess yourself up. So I would just say plus V4 Henry minus V5 Henry. Is that the right one? Excuse me, I should say minus V6 Henry and then minus V5 Henry. If we're going clockwise around that loop. Sum those up and I get 0. Okay, now notice we've already done V6 Henry and V5 Henry. We can just substitute those. Here's V6 Henry, needs to go right there. And see, you can see where the error can so often be because that minus is in front of it, and all of those terms in that V6 Henry would need to have the minus sign there. That's where all those little, checks that you have to do would come into play. And so, hey, if you do it this way, I think it's much simpler. You're going to not have that problem with having to follow those rules so carefully when you just back substitute it, because you already solved for it once and made it easier on yourself. And then also we have to substitute this V5 Henry right there. So the only one we don't have is the V4 Henry, and let's get that. So what is V4 Henry? Well, we already satisfied the passive sign convention because we labeled the plus of the V4 Henry with the dot. And so we just need to go, excuse me, that's not correct what I said again. I keep wanting to think about the mutual inductance term. We have labeled the V4 Henry with the dot, and that's good for the mutual inductance terms where we've used it before, but what we also need is to satisfy the passive sign convention for the self-inductance terms. So that means we need the current to go into the plus, and into the plus would be I2, and that's the only one, and it is going into the plus. So that would be is it J8? J8 times I2. And then we have the mutual inductance terms. Okay, we have the J4 ohm mutual inductance, so plus J4. And we need the current going into the dot of that J4 ohm inductance. Well, into the dot, I3 is going into it, I2 is going against it, so the net current going into the dot is I3 minus I2. And if we do that, then we'll put a plus there. And then I have the J6 ohm mutual term with the 5 Henry inductor there, so plus J6, and then I need the current going into the dot of that one, and if I have that, then I'll put a plus sign, so the current going into that dot, I1 is going into the dot, I2 is not, so the net current going into the dot is I1 minus I2. And so that's my term for V4H. So that last equation should become 4I2 plus J8I2 plus J4I3 minus I2 plus J6 I1 minus I2. Okay, then I've got to subtract off V6 Henry, so I'm going to put minus, and I'm going to put a big bracket here. And V6 Henry is J12 I3 minus I2 and plus J4 I2 minus J0, which obviously, again, we don't need to include that term, I1 minus I2. Close that bracket. And then we need to subtract off V5H, so I'll put that down here, minus, I'll open another bracket, and V5H is J10 times I1 minus I2 plus J6 times I2 so J10 I1 minus I2 plus J6 I2 plus J0 I3 minus I2. And that equals 0. So notice, you can see if you try to use those rules directly, you can do it, but I think you have to be so super careful with how everything is done. So I really advocate using, mesh analysis for a lot of these mutual inductance problems, labeling the voltages such that the plus is with the dot, so you're sort of satisfying the dot convention, and then using the mesh analysis to make sure the currents, for the self or mutual terms are going into the dot or into the plus, so that we satisfy the dot convention and the passive sign convention for the mutual terms and the self terms. Now, I'm not going to go through and solve this, but I hope you can see we have 3 equations. So here's our first equation. I'll say one, and it has mesh currents. Oops, no, that's not 1. Excuse me. 1 is right here. It has mesh currents I1, I2, and I3, which we don't know. And then here's our second one, 2, and it has mesh currents I1, I2, and I3 in it. That's still it. So now we've got 2 equations but 3 unknowns. And then now we have a third equation, I1 and I2 and I3 are in it as well. So 3 equations, 3 unknowns. We know we can solve for I1, I2, and I3 from star 1, star 2, star 3. And once we get those mesh currents, then we can find anything we want relating to the circuit in general. And then, the only thing you might have to do is, obviously, if you want something else, like a voltage or a current in the time domain, you may have to go, from the phasor domain back to the time domain. Now obviously you can see that solving some of these mutual inductance problems, they're going to take time unless it's just a simple maybe two-loop problem, because you're going to have to get all those terms and then solve for several things. So be aware that I probably will have a mutual inductance problem that is not all that difficult to do, but I very well I may like a problem like this one where I want to test you with, can you get the currents, or can you get the equations that you need to solve, sort of like I've had with the supernode and supermesh circuits. Can you get the specific equations that you need to solve the problem, not necessarily can you solve the problem, because obviously that can be a little bit cumbersome on a test. So anyways, that's one example problem of mutual inductance, and I hope that helps you understand how to, I think, appropriately go about and solve one of those types of problems.